Hi everyone, I'm Penny from AMD. I am a senior software working for GPU virtualization on RISC team. Lately, I'm working on enabling a new CPU frequency driver on Xen. Maybe some of you have already seen my patch serial, and today I will do a brief introduction on it. Right now, Xen only provides ACPI P-States CPU frequency on AMD platform. It manages CPU frequency with switching only in three P-States. Comparing with that, the new CPPC, the full name is Collaborative Processor Performance Control, introduced a continuous, abstract, unitless performance scale. It is an ACPI standard and provides finer grain frequency management. ACPI specification does not mandate a specific range of values to be assigned to this scale. It only defines several points, which I already drew in the picture. The highest perf, the nominal perf, the lowest nonlinear perf, and the lowest perf. Software could read them to comprehend the limits of managed performance range. Highest performance corresponds to the highest boost frequency state. It's like the legacy boost state. This state is not sustainable and can be achieved only opportunistically, depending on infrastructure constraints. Nominal performance is often referred as the highest sustained performance level of the processor. It corresponds to the base frequency P state P0, and for lowest nonlinear performance, it could be interpreted that only above this threshold, lower performance levels should be generally more energy efficient than higher performance levels. It is equivalent to the idle frequency. In traditional terms, it represents the P state P2. The last is lowest performance. This is the lowest performance level of the processor. It corresponds to the lowest power at which the processor can perform computations. The right figure shows an overall end-to-end solution architecture for CPPC. I will introduce them layers by layers. At the bottom of the framework is the SMU firmware. It will help translate the CPPC requests into the frequency levels. And it has built-in dynamic frequency control algorithm. What SMU exposes to the Xen driver is the CPPC MSR register layer. Here I haven't listed all the MSR registers, just the two commonly used ones, CPPC Capability 1 and CPPC Request Register. Driver firstly need to read the CPPC Capability Register to know this platform's performance capability. The highest, the lowest, the nominal, and the lowest nonlinear. On runtime, the driver needs to parse performance goals, hints to the SMU through CPPC request register, including minimum, maximum performance limits and preference towards energy efficiency or performance, abbreviated as EPP. Above the CPPC MSR layer is the Xen driver, as the CPPC could run in two different modes, passive mode and active mode. We need to implement two different new CPU frequent driver, amd-cppc driver for the passive mode, and amd-cppc EPP for active mode. Finally, at the topmost layer is the operating system and user space. There are two entries in the ACPI table which are essential for the CPPC mode. The CPC entry and the PSD entry. The existence of the CPC entry in the detected processor is the key flag to tell whether the platform supports CPPC or not. The PSD entry is also needed to represent logical processor dependency. However, both entries live in ACPI dynamic map table, which then could not parse right now, so we need to rely on DOM0 Linux kernel to do the interpretation work and parse the required CPC data to the Xen driver, where the newly ended hypercore Xen PM CPPC. In user space, we have specific comments in Xen PM tool for users to set the CPPC values to match their application needs, or read your platform CPPC capability. I will briefly introduce the following key CPPC concepts to help you understand how CPPC works. The first one is about CPPC enablement. You need to know that only one driver sets the CPPC enable bit in CPPC enable MSR. The SMU firmware could start to accept messages through CPPC request MSR and utilize the CPPC algorithm for performance and power optimization. And only when enable bit gets set, the SMU firmware will program the capability register for the drivers to read. Like I said in previous, AMD-cppc has two operation modes, passive mode and active mode. In passive mode, we still rely on Xen governor to do the performance monitoring and tuning. Each time when the governor calculates a desired performance, and it will write it to the request register. SMU will accept it and translate it into actual hardware states, like core frequency. So it's very alike traditional discrete P-States model, but with continuous scaling. In active mode, is totally different. The Xen governor is not needed anymore. The SMU firmware will decide frequency at 1 millisecond time scale based on the workload utilization, usage in other IPs, infrastructure limits such as power, thermals, and EDC. In this mode, the SMU will ignore requests done in the designed performance target and takes into account the values set to the minimum request performance, maximum request performance, and energy performance preference. The minimum and maximum are easily understood. But for energy performance preference, called EPP, is a new concept. It is used in the CCLK DPM controller to drive the frequency that a core is going to operate during short periods of activity, which we call it the minimum active frequency. EPP scales the mean active frequency linearly between idle frequency and Fmax range. An EPP of the lowest value could be 0, sets the mean active frequency to Fmax, and an EPP of 255, the highest value, sets the mean active frequency to the idle frequency. It is a very abstract value, so we defined 3 different performance policies in Xen codes. They are power safe, on-demand, and performance. It will help users to determine the power perf trade-offs their platform needs. These are the detailed performance policy settings in active mode. You could see that in PowerSafe, the EPP is set with the 255, the highest value, and we lower the maximum to equal with the minimum for achieving the utmost power savings. And in performance, the EPP is set with 0, the lowest value, indicating instant CCLK transition, and the minimum is increased to equal with the maximum for achieving the utmost performance. In on-demand, in order to show no preference over power save versus performance, the EPP is set with the medium value. And for minimum and maximum, they are both set with the platform capability. In passive mode, we have discussed before, the Xen governor is still kick in, and once upon a time, the Xen governor will calculate the designed performance. The driver needs to write it to the request register. The SMU firmware will pull for the request register for all cores and threads on every DPM circle. After it reads the designed performance, it needs to do the translation. So the formula here is to convert a CPPC perf value to the frequency in SMU. And will the CPPC max point to the highest perf in the platform? And Fmax means the max frequency, Fmin means the idle frequency. The formula shows the linear scaling. You could see that. So the highest perf corresponds to the max frequency, and the nominal corresponds to the base frequency, and the nonlinear corresponds to the idle frequency. Let's go back to the active mode again. In that mode, where the governor is not needed and hardware will independently select a performance level appropriate to the current workload. But still in this mode, the driver still needs to provide several hints that guide the SMU performance level selection, including the minimum, maximum performance limits and the EPP. I have drawn this picture to show you how these CPPC parameters affect the CCLK DPM frequency. You could assume it as a core frequency here. The lowest point in the picture is referring the idle frequency. The idle frequency can be changed by the increasing CPPC minimum register. Near it, we could see an instant transition, and that slope means the mean active frequency. It points to the frequency that the core will operate once the controller observes any activity, when the CPU core decides to leave the idle frequency, and it is controlled by EPP. It is a linear scaling between the Fmax and the idle frequency. Here you could see it is set with the medium value. The peak in the picture points to the max frequency, and it is influenced by the CPPC maximum register. This slide is about the detailed implementation in Xen. I have implemented two new CPU frequent drivers, amd-cppc for passive mode and amd-cppc EPP for active mode. The major codes live in a new C file called amd-cppc under CPU frequent subdirectory, and all codes are guarded by the config amd. The new CPU frequent driver must be enabled explicitly in Xen CMD line during boot time. If you want the passive mode, you need to write CPU frequent equals amd-cppc. If you want the active mode, you need an extra active anchor. amd-cppc driver is responsible for implementing CPPC in passive mode, which still leverage Xen governors such as on-demand performance power sieve to manage and monitor the performance. So users could still use the set scaling governor, then PM subcomment to set their performance policy. amd-cppc EPP driver is for the active mode, and it doesn't need the governor anymore, and it relies on hardware built-in CPPC power algorithm to automatically calculate and choose the CPU frequency. We have provided three different performance profiles: on-demand performance and power save. We have specific CPPC setting, then PM subcomment, the set CPU frequency CPPC for users to choose their preferred performance profile. Users could still use the governor setting comment to provide performance policy too, but it is not recommended. Nevertheless, the governor thing does not exist in concept level in active mode. And users could still use Xen PM get CPU frequent parallel to acquire the CPPC capability and status. The whole implementation, I hope it will be available in Xen 4.21. I still have a few commits behind, and I will try to catch the deadline. And this link here is the version 8 serial patch serial if you are interested. I'm not going to run a live demo here since I'm remote. I write a very simple sampling script for anyone you are interested to see the performance change for CPPC in active mode. In here, I firstly set all CPUs in power sieve policy, and we will do 60-second sampling. Then we change the policy to the performance policy, and we will do another 60-second sampling. The red picture is a snippet of the output in my test board, and you could see very apparent frequency change. And the last slide is about what's missing. So actually, there are two types of hardware implementation for amd-cppc. One is full MSR support. This is a type we support in Xen 2. And another is shared memory support. It exists in some very beginning prototype, like Matthews. So, but if we want to support shared memory, we need ACPI P-States framework supported in Xen first, and it's kind of difficult to support from my view. Another missing concept is preferred core support. We know that not all cores are able to reach the maximum frequency, respecting the infrastructure limits. So AMD redefined the concept of maximum frequency of a part. This means that a fraction of cores can actually reach the maximum frequency. And these require to then to redesign their scheduler to allow the platform to specify an order of preference that processes should be scheduled on the different cores. Yeah. So it means either we redesign the existing scheduler or we create a new scheduler for it. So that's all for my presentation here about the AMD CPPC. Any question?